Assalamualaikum and salam sejahtera. So now we are at chapter 7, optics. So this is the longest chapter for the second semester, and we have a biggest marks allocation for this chapter. So basically we have 9 subtopics to cover for this chapter. That is started with 7.1. It is reflection at spherical surface. So for this subtopic, we have the mirror equation, because reflection happens at mirror. So 1 over f is equal to 1 over u plus 1 over v. And we have also the equation of magnification. Okay, m equal to negative u over v and hi over ho. And also we have the relationship between the radius and the focal length. When we go to chapter 7, the most important thing is to look at the sign convention when we do calculation. So for image distance v, we have, if the image distance is positive, meaning that the image is real and inverted, and if it is negative, means it is virtual and upright. For focal length, for concave mirror is positive and convex mirror is negative. And for the value of magnification, we have two interpretations. So first, in terms of sign, is either positive or negative. M positive means the image is virtual and upright, and if the M magnification is negative, means the image is real and inverted. So if you could realize here, the sign convention for M and V is different. Another interpretation that we can do for the magnification is on the value of M. If the value is bigger than 1, it is magnified. If it is diminished, it is smaller than 1, and if it is equal to 1, it is same size. So for example, you have the value of m is equal to negative 0.7. Negative means the image is real inverted. 0.7 means the image is smaller than 1, so it is diminished. From one value of magnification, we can know 3 characteristics of image. For example, for this number here, we have m is real, inverted, and also diminished. That is for 7.1 reflection. So reflection happens at convex and concave mirror. Then for the second subtopic, we have refraction, the other light phenomenon. So it is refraction at spherical surface, and this is the equation of refraction at spherical surface. So we have n1 over u. n1 is where the object is, the index of refraction for the position of the object. Then n2 is the refractive index for the other medium, and r is the radius of curvature. So the most important thing that you have to consider when using this equation is the sign convention for radius of curvature. So we have if your if your refracting surface is convex, means your r is positive, and if your refracting surface is concave, means r is negative. So it depends on where your object is. Concave or convex is determined from the object's point of view. So for example, if the object is at this position, so it's a convex surface. But if the object is at this position, so from the object's point of view, so this is a concave surface. So that is 7.2. For 7.3, thin lines equation, we go to lines. So this time again, we still focusing on the light phenomenon of refraction. It's the same as the second subtopic discussed earlier. So we have thin lines equation is just basically equal to the mirror equation. Okay, so 1 over f equal to 1 over u plus 1 over v. We can also talk about the magnification for thin lines. The sign convention is equal. Okay, so basically this table is just equal to the table up here from the first subtopic table here, but the difference is at the sign convention of f, because for lens, the convex lens will have positive focal length, but for concave lens it will have negative focal length. So it's not the same as mirrors, it's going to be the other way around. For 7.3, we also have another equation for lens, that is lens maker's equation. It's lens maker's equation. So it's 1 over f equal to n lens. So index of refraction of lens per medium, and medium minus 1 over r1 minus 1 over r2. So in terms of the sign convention, it is just the same as the previous equation, that if it is convex surface, so r is positive; if it is concave, it is negative; and if the surface is flat, so the radius of curvature is infinity. Let us take two types of lens for example, to discuss about the sign convention. So let's say we have here concave lens. So the light is coming from the left. So this is your R1. So from the left, it is seen your R1 is concave, means that if so R1 is negative, and as it goes to the second surface, light is coming from the same side. So your R2 is convex, so R2 is positive. And if you take the next example, this is convex meniscus. So we have here R1 is convex, so it is positive, R1 positive. R2 is also convex, so R2 is also positive. Then for chapter 7, starting from 7.5, 7.6 until 7.9, we are talking about the light phenomenon of interference. So there must be at least 2 or more light to interfere. So the first case, altogether we have 4 cases that is started with Young's double slit experiment, then interference in the thin film, then diffraction by a single slit, and last one is the diffraction grating. Let us go one by one. So we have Young's double slit. We have 2 types of interference, that is constructive and destructive. So constructive will produce bright fringe, and destructive will produce a dark fringe. And this is the equation. We have m lambda d over d for constructive. Or the other term that we can use for constructive bright is maximum interference. And for dark destructive, we have minimum as the other term that we can use, minimum interference. So it is giving us the same meaning. So for minimum interference or destructive interference, the equation is just about the same, but the part that is different is at the number of order, m plus half for destructive interference. We also have another equation, delta y. So delta y here is the separation between 2 consecutive dark or bright fringes. If we refer to the interference pattern produced by the Young's double slit interference of light, so this is the interference pattern of Young's double slit. So the width of the bright and dark fringes here is just the same. So the distance between dark to the next dark is delta y. That is what is meant by delta y. Or it can be from bright to the next bright is also delta y. So in one pattern we're actually having so many delta y, or we call delta y as fringe width. Then we have interference in thin film. So basically the first thing that we need to do is we have to look at the case we got. It's either it is in phase or anti-phase. So we have 2 possible cases of thin film. So if it is in phase, meaning that it is for example, we have upper here, this is our thin film. So there must be, for example, here is 1, here is 1.3, here is 1.5. So the bottom medium must be bigger than the upper medium here, and the middle medium of thin film must be bigger than the index of refraction of the upper one, okay, the top one. For the case of in phase, this is the equation for constructive and destructive, And if it is the case of antiphase, so this is the equation for constructive and destructive. So if you could compare for constructive in phase, the equation is equal to destructive antiphase. Okay, please remember that in your exam the formula is given, but we only have two formula, this one and also this one. So you need to know that these two formula is actually for two cases, that is constructive destructive for in phase or antiphase. Then the next case is diffraction by a single slit. So for single slit we have few equations. For dark fringes, we have y equal to m lambda d over a. And for bright, we have m plus half lambda d over a. So if you could compare with the double slit, it is the other way around, meaning that equation for constructive double slit is more or less equal to equation for destructive single slit, so m lambda d over a. We can also have the equation in terms of the angle, a sin theta equal to m lambda for destructive or for dark, and a sin theta equal to m plus half lambda d over a is for bright fringes. Okay, so a here is known as the slit width. We only have one slit, single slit. And if the question asks us to find the width of the central maximum, so we will use this equation. So basically this equation is actually coming from width 2y1 for dark. So you have 2 lambda d over a. And also you are possibly asked to find the angular width. So for the angular width is 2 theta 1. Okay, 2 theta 1. So theta 1, you can get it from the equation that contains angle. Okay, and last one is diffraction grating. So for diffraction grating, you have the basic equation is d sin theta equal to m lambda. So it is all written here. Theta m is the mth order for diffraction angle. Is number of order, wavelength. D is the slit separation. And the other term that we can use for d is equal to 1 over n. Our big N here is the number of lines per unit length. So that's all for chapter 7, and hopefully you can have a fine revision for this chapter. Thank you very much.